All right, let's jump into the world of circular motion. And we're not just talking theory here. We've got a 3D simulation
Mhm.
to really bring this concept to life.
Yeah, it's from a website packed with open educational
I
resources.
was playing around with it earlier. It's amazing. You can actually tweak variables and see what happens.
Exactly.
And for those who want to follow along at home, the link is in the show notes. But imagine this. A mass is spinning on a tabletop,
Okay.
and it's connected by a string to another mass that's hanging down below.
Oh, I see where this is going.
And that hanging mass,
Yeah.
it's the key to something called centripetal force.
Right.
Now, I remember that term centripetal
Hmm.
force from physics class,
Mhm.
but if I'm honest, it always sounded a bit mysterious.
Well, it's basically what keeps things moving in a circle.
Oh, so without it, that mass on the table would just fly off in a straight line?
Exactly. Think of it like swinging a ball on a string.
Okay.
Your hand is providing the inward pull, that's the centripetal force.
I'm with you.
But the moment you let go of that ball, it's going to go off on a tangent.
So it's like this invisible tether constantly pulling the object towards the center of the circle.
Precisely. And there's a formula that describes this force, F mv2r.
Okay, break that down for me. What does each variable represent?
So m, that's the mass of the object v, is its velocity, and r is the radius of the circle.
So the faster something is moving or the tighter the circle, the more force you need to keep it on track.
That's exactly it.
Ah.
And that's why taking a sharp turn at high speed in a car can be so dangerous.
Right, because the smaller the radius, the more force is needed to keep the car from veering off the road.
Exactly.
Wow, I'm starting to see how these concepts have real-world implications.
Absolutely.
I love it when we can bridge that gap between theory and practical application.
It's what makes physics so fascinating.
Okay, so back to our simulation. What else can we learn from this model?
Well, it also highlights the concept of angular momentum.
Okay, and angular momentum is like...
It's kind of like the rotational equivalent of linear momentum.
Uh-huh.
You can think of it as an object's tendency to keep rotating.
It's like a spinning top that just keeps going and going.
Exactly. And just like linear momentum, angular momentum is conserved in a closed system, which means it stays constant.
Right.
In this simulation, it's represented by the formula L equals mr2o.
And I'm guessing that m is still mass and r is the radius. What about that o?
That's angular velocity.
So how fast the object is spinning.
Precisely. Now, here's the interesting part. Because angular momentum is conserved, if we change the radius, something else has to adjust to compensate.
Okay, I'm following you.
Let's play around with the simulation a bit. What do you think will happen if we make the circle smaller by decreasing the radius?
Let me think. If the radius gets smaller and angular momentum has to stay the same, I'm going to guess that the mass has to spin faster to make up for it.
Let's test your theory. Go ahead and shrink the radius in the simulation.
Whoa, you're right. It's speeding up.
Yeah.
That is so cool to see in action. So that's how angular momentum stays constant. Even when one thing changes, the overall quantity remains the same.
Exactly. That's just a glimpse of what the simulation can show us.
I'm excited to keep exploring it.
Now, let's get a little more adventurous. What do you think happens if we play around with the hanging mass, the one that's providing that centripetal force?
Okay, now we're getting into the fun stuff. Let's do it. So we're going to make that hanging mass heavier. What happens then?
Well, remember, the hanging mass is what's providing that inward pull, the centripetal force that's keeping the rotating mass moving in a circle.
Right.
So if we make it heavier, we're increasing that force.
So I think the rotating mass would just spin in an even tighter circle?
That's a good guess, but here's where things get a bit tricky.
Okay.
When we increase that hanging mass, it's like giving that rotating mass a sudden jerk inwards,
I see.
and it actually overshoots that circular path.
Oh, interesting.
And it moves closer to the center. But then something else happens.
What's that?
As it gets closer to the center, the radius of its motion gets smaller.
Right, smaller radius.
And we just learned that when the radius decreases, the angular velocity has to increase.
To keep that angular momentum constant.
Exactly. So now the rotating mass is moving faster, and that increased speed causes it to swing back outwards away from the center.
I see.
And then the whole cycle starts over again.
It's like a constant back and forth.
It is, and we call this motion oscillation.
Oscillation.
It's all about the system trying to find a new balance, a new equilibrium when the conditions change.
That makes sense, like pushing someone on a swing.
Yes. Great analogy. You push them, they swing out, gravity pulls them back down, and they swing back towards you.
It all comes back to those fundamental forces.
And that interplay of forces is what creates that rhythmic, back and forth motion.
I'm already looking at swings differently now.
And those giant swinging pirate ship rides at amusement
Oh
parks,
yeah, those are intense.
it's all about that same interplay of forces.
That's amazing. This is making me think about all sorts of things.
Mm-hmm.
Okay, so we've played with the hanging mass. What about the rotating mass itself? What if we change that?
Well, remember how we talked about the simulation being designed to maintain that circular motion? It's actually quite clever. If we increase the rotating mass, the simulation will automatically adjust the hanging mass to keep things balanced.
Oh, so they're connected. Like they work together to make sure that rotation stays smooth.
Exactly. It's like they're partners in a dance, constantly adjusting to each other's movements.
I love that analogy. So if one changes, the other one has to compensate to maintain that perfect circular motion.
Exactly. It's like a built-in feedback system.
It's pretty amazing how this simulation captures these complex interactions.
It really highlights the interconnectedness of these concepts.
Right, it's not just one thing happening in isolation.
And you know what? The same thing happens if we change the radius of the circle.
So no matter what we tweak, the simulation is always working in the background, upholding those laws of physics.
Exactly. And it emphasizes that in physics, a change in one variable will always affect the others.
It's like a domino effect.
And that's what makes it so fascinating. We can see these principles at play everywhere, even in seemingly simple things like spinning an object.
Right. And this deep dive is really opening my eyes to the beauty and complexity of circular motion.
I'm glad to hear that, because once you start looking for it, you'll see circular motion everywhere.
Yeah, like bicycle wheels, ceiling fans, those spinning teacup rides at amusement parks. It's everywhere.
And each of those examples can be analyzed using the very concepts we're discussing today. Centripetal force, angular momentum, the relationship between velocity, radius, and acceleration.
It's incredible how these principles apply to such a wide range of phenomena.
That's what I love about physics. It's like a universal language that helps us understand the world around us.
You know, we've been talking about horizontal circular motion, that mass moving on a flat tabletop.
Right.
But what if we tilted that table? What if we introduced a vertical component to the motion?
Now you're thinking outside the box. That's where things get even more exciting.
It's like those pendulum rides that swing you back and forth.
Exactly.
It's not a perfect circle, but it's definitely circular motion.
Absolutely. And that's a perfect segue into our next exploration.
I'm ready to dive into the world of pendulums. Let's do it. All right, so we're thinking about a pendulum swinging back and forth. I can kind of see how it's moving in a curved path, but how does this connect to what we've been talking about with horizontal circular motion?
Well, it's all about breaking down that motion into its parts.
Yep.
Like, imagine you freeze the pendulum at one point during its swing.
Got it.
At that moment, its velocity has two parts.
It's two parts.
One that's pushing it sideways horizontally, and the other pulling it up or down vertically.
Ah, so it's like two different motions happening at the same time.
Precisely. And it's that horizontal component that's giving us that circular motion, the part that's keeping the pendulum bob moving along that curved path.
Okay, that makes sense. But what about that vertical component? That's got to be affected by gravity, right?
Exactly. Gravity is why the pendulum speeds up on the downswing and slows down as it swings back up.
Right, gravity.
But now let's think about centripetal force.
Okay, how does that fit into this picture with the pendulum?
Remember, in horizontal circular motion, the centripetal force was always pointing toward the center of the circle.
Yeah, I remember that.
Well, with a pendulum, the direction of that force is constantly changing.
Oh, that's right. But why is it changing?
Because centripetal force always acts perpendicular to the object's velocity.
Okay.
And with the pendulum, that velocity is always changing direction as it swings.
Right, that makes sense.
It's like the force is always adjusting to keep the pendulum on track.
So how does it actually manage to keep that pendulum moving in that smooth arc if the force is always changing?
Well, the centripetal force isn't just one force. It's a combination of forces working together.
I see.
In this case, you've got the tension in the string, which is pulling the bob inwards.
Right.
And you've also got a component of gravity that's acting towards the center of that arc.
So those two forces, they're working together to keep that pendulum swinging.
Exactly. They're constantly adjusting their pull to make sure the pendulum follows that predictable path.
You know, this makes me think about those carnival rides where they spin you around and then tilt you up at an angle.
Oh, yeah, those are fun.
It's like they're playing with the direction of that centripetal force to create those crazy sensations.
You got it. They're introducing a vertical component just like our pendulum.
And that's what gives you that feeling of weightlessness or like you're going to fly out of your seat.
Exactly. Physics in action.
I never thought about those rides like that before. This whole deep dive has been a real eye-opener.
It's amazing how these concepts apply to so many things around us.
I'm already looking at the world differently.
That's what we hope for, to inspire that sense of wonder and curiosity about the world.
Well, I think we've definitely achieved that today. I feel like I've gone from basic formulas to really understanding how circular motion works.
That's fantastic to hear.
And you know what? I bet our listeners are feeling the same way.
We hope so.
So the next time you see something spinning, think about those forces at play, those principles that are governing its motion.
Whether it's a toy or a giant Ferris wheel, there's physics happening all around us.
Exactly. Keep those minds curious, folks.
And until next time, keep exploring.
That's a wrap on our deep dive into circular motion. We'll catch you on the next episode of The Deep Dive.